Well, yesterday's discussion was on kinetic energy, which is energy of motion. Today's discussion is on potential energy. And potential energy is energy that is stored for later use. So as an example, if you had breakfast this morning and you stored the energy from that food in your body, and now you're going to be utilizing that stored energy to maybe work some physics problems in a little while. You're going to be maybe playing baseball later this afternoon, and so the stored energy from the food that you ate for lunch is then going to be utilized to do work on the baseball bat and the baseball and moving your body from one base to the next. So that is stored energy that you later utilize. If your parents have a car, then hopefully there's some gasoline in it, and that gasoline is stored energy to be used for later work to move the car from one place to another. The main type of potential energy that we're going to be discussing today is called gravitational potential energy. And that energy is energy that an object has due to its position above the earth. So if I have this big heavy book and I hold it maybe just a couple of inches off the ground and I drop it, it's going to make a noise. It's going to make if I drop it on your foot, you're going to notice it. However, if I hold it way up here and then I drop it, and it lands on your foot, you're definitely going to notice that it hit your foot. I think you'd much rather me drop a big heavy book on your foot from, maybe this far above your foot for maybe just a couple of inches, as opposed to if I hold it way up here above my head and then drop it on your foot. So the higher something is above the ground, the more it has the ability to do work. Well, why is that? Well, because gravity is a force of acceleration. And why let that book go? We already talked about how gravity is going to accelerate it down towards the earth. And the farther it has to go, the bigger the acceleration can get, because the longer it's under that acceleration, so the bigger the velocity can get by the time it hits the ground. We talked about acceleration and we talked about velocity previously, so hopefully that's not a foreign concept. So if I just drop it a little short distance, it doesn't have much time to accelerate, so the velocity can't get very big. If I drop it from way up here, it's got a much longer time to accelerate, so the velocity can get much higher. And we talked yesterday how kinetic energy is very much related to velocity, and the bigger the velocity, the more energy it has and the more work that it can do. Okay, so when I talk about gravitational potential energy, I calculate that by taking the mass of the object, multiplying it times the acceleration due to gravity, and the height that that object is off of the ground. Gravity on Earth accelerates at a rate of 9.8 meters per second squared. So as you're making your flashcards with all of the formulas on it for this particular chapter, make sure that you include this number on it as well. That's not something I expect you to have memorized, although you may use it enough that you may have it memorized by the end of the chapter. Go ahead and put that on your flashcard that you're making with all of your other formulas on it, just as you've been doing for the other chapters. Okay? So we discovered with kinetic energy that velocity is actually a much bigger factor than mass is, because we have to square that velocity when we calculate energy. But let's see if any one of these factors is going to make as big a difference in potential energy. Now, gravity is going to obviously make a difference, because if you're standing on the moon and you drop that big heavy book, the acceleration due to gravity is much smaller, and so it's not going to gain as much velocity as it drops as it's going to be here on Earth. Now, if you're on Jupiter and you drop the same book, the acceleration due to gravity is much, much higher, and so it's going to hurt a lot more when it falls on your foot. But for everything that we're talking about while we're on Earth, the gravity is going to be uniform, so it's not really anything that is going to concern us as far as purposes of this class go. Okay, so let's compare dropping a 10 kilogram hammer with a 5 kilogram hammer, and both of these hammers are located 2 meters above the ground. And let's see how much potential energy we end up with. So potential energy is the mass so that's 10 kilograms, times gravity, and we're assuming we're on Earth, so that's 9.8 meters per second squared, times the height above the ground, which is 2 meters, okay? So the potential energy of this, if I take 10 times 9.8 times 2, I'm going to end up with 196 joules. I do want to point out that most of the time, the measurements that we take are measurements from the ground up. We could define that place as something a little bit different. We could define it as like if I had maybe a chair sitting right here in front of me, and I just drop the book onto the chair, then maybe I only want to measure the height from the chair if the book can't fall any further than that. So you can change that reference point if you need to. Again, most of the time for the purposes of this class, we're just going to assume that we're going from the ground. Okay, so in fact, I'm going to move my line over a little bit here because I didn't quite allow myself enough space to write this down, did I? Okay, so now let's look at this 5 kilogram hammer. Potential energy for the 5 kilogram hammer is going to be 5 kilograms times gravity, 9.8 meters per second squared, times 2 meters. And so this time the potential energy is going to be 98 joules. So you can see that, again, they're both 2 meters above the ground. So the height was the same. The mass got multiplied by a factor of 2 because 10 is twice as big as 5. So if I have 2 times the mass, that's going to lead to, well, 98 times 2 gives me 196. So 2 times the mass will give me 2 times the potential energy, okay? So that was similar to how we discovered that mass worked in kinetic energy. Let's see how the height works now in potential energy and see if it's a bigger factor. If you had to guess, what would you think? So stop just for a second and look at the formula and say, okay, do I think that it's going to make a bigger difference than the mass would? Okay, you have an answer in your head? Let's calculate it and see what we find out. So potential energy, now I'm going to take a shortcut here because I already had a 5 kilogram hammer at 2 meters and I already calculated the potential energy. So I already know that it's 98 joules. So I'm just going to copy that over here since I already did it over here. Okay, now let's say that I have, I'm comparing here, I have 2 5 kilogram hammers. One's at 2 meters and the other one's at 1 meter. Okay, so they're a difference of, this one's twice as high as this one is. So let's check this potential energy now. So the mass is 5 kilograms. The gravity is 9.8 meters per second squared. And the height is 1 meter. And so when I calculate that, that is going to give me 5 times 9.8 is going to give me 49 joules. So again, 49 is half of 98 and 1 meter is half of 2 meters. So once again, if I go 2 times the height, that's going to lead to 2 times the potential energy. Hopefully you were able to see that because our kinetic energy equation did have a squared sign in it, and there is no squared sign in this, so it would be hopefully more logical that multiplying the mass by 2 or the height by 2 is going to give me twice the potential energy no matter what the case is. Okay, so there's some examples of how to work potential energy problems, and so we'll be working on that today, and then after that we're going to be combining the two of them together.